All right, today we're going to dig into one of algebra's most famous formulas, the binomial theorem. Now, you probably remember it from math class, but trust me, behind that formula is a pretty amazing story about discovery and a hidden pattern that connects algebra to the real world of probability. So let's just dive right in with a question. How would you expand a plus b to the 12th power? I mean, really think about it. If you tried to multiply a plus b by itself 12 times by hand, well, you'd be here for a very, very long time. It gets messy fast.
Expanding it to the power of 2? That's pretty easy. Most of us have this one memorized. A squared plus 2ab plus b squared. Simple enough. What's kind of wild is that this exact formula was written down by the Greek mathematician Euclid way back around 300 BC.
Okay, so let's go one step further to the power of 3. It's a bit more work, sure, but it's totally manageable. You multiply the terms, you combine the like ones, and you get a cubed plus 3a squared b, and so on. But you can already feel it, right? You can feel it getting more complicated. Because as that exponent gets bigger and bigger, the whole process just explodes. It goes from being a little tedious to being practically impossible to do by hand. And this was the exact problem that mathematicians stumped for centuries. I mean, there just had to be a better way.
And thankfully, for all of us, there is. A really beautiful and, believe it or not, a surprisingly simple pattern. It was discovered and then rediscovered all over the world for hundreds of years, and it gives us the shortcut we've been looking for.
And the journey to figure this out, it wasn't just one person. It was more like a global relay race over centuries. It starts with Euclid in Greece, then the torch gets picked up by the Persian poet and mathematician Omar Khayyam. Then the pattern shows up in a diagram in 14th century China. It's famously studied by Blaise Pascal in France, and it's finally polished into its modern form by Isaac Newton. So, what is this incredible pattern? Okay, let's strip away all the variables, the a's and b's, and just look at the numbers out in front, the coefficients. When we do that, something really cool happens. For the power of 0, you've got a 1. For 1, it's 1 and 1. For 2, it's 1, 2, 1. For 3, 1, 3, 3, 1. And for 4, 1, 4, 6, 4, 1. Are you seeing it yet? What pops out is this really elegant structure, which you might know as Pascal's triangle. And the rule to build it is so simple. Each number is just the sum of the two numbers right above it. I mean, look at that row for n equals 4. You see that 1 plus 3 gives you 4, and 3 plus 3 gives you 6. That's it. That simple little rule generates every single coefficient you'll ever need.
So here's the bottom line. The shortcut for expanding any of these things comes down to two simple, predictable patterns working together. First, you just grab the coefficients you need from the right row in Pascal's triangle. Second, the powers on the letters follow this nice little dance. The exponent for a starts high and counts down, while the exponent for b starts at 0 and counts up.
Okay, this is a fantastic shortcut, right? But what do these numbers actually mean? Like, why is there a 6 in the middle of that row? What's so special about 6? Well, the answer isn't just in algebra. It's in the mathematics of choosing things. It's called combinatorics. See, every number in Pascal's triangle has a special name. It's a binomial coefficient. Now that sounds fancy, but it's often written as n choose r. And it does, well, exactly what it sounds like. It tells you the number of ways you can choose r things from a bigger group of n things.
Let's make this real. Forget the formulas for a second. Imagine you have 4 weasels, yep, weasels, named A, B, C, and D. And you need to pick a team of 2. How many different pairs can you possibly make? Well, you could have A and B, or A and C, or A and D, and if you list them all out, you'll find there are exactly 6 ways to do it. And there it is. That is 4 choose 2. It's the same 6 from Pascal's triangle.
And that right there is the big aha moment. The binomial coefficient is just a shortcut for counting. The reason the number in front of a squared b squared is a 6 is because there are exactly 6 different ways you can pick 2 b's out of the 4 factors you're multiplying. The pattern isn't some random math magic, it's literally just counting.
So we have the coefficients from Pascal's triangle, and we now know they're just a way of counting combinations. And we have that nice, predictable pattern for the exponents. So let's put it all together and build the official theorem.
And here it is, in all its glory. Now, I know it might look a little intimidating, but it's really just a super compact way of writing down everything we've already figured out. That big sigma symbol, it just means add up all the terms. The part that says n, k, that's our n choose k counting shortcut.
And the a and b parts are just doing that descending and ascending exponent dance we talked about.
Let's see it in action with a plus b to the 5th power. First, we go to the 5th row of Pascal's triangle to get our coefficients. 1, 5, 10, 10, 5, 1. Easy. Then the powers of a count down from 5. The powers of b count up from 0. We just stick them all together and bam! There's the full expansion, and we didn't have to do a single bit of boring multiplication.
Okay, so who cares, right? Why does this algebra formula from hundreds of years ago still matter today? Well, it's because this theorem is actually the engine that runs behind the scenes for calculating probabilities in a ton of real-world situations.
Here's the connection. When you calculate a probability, it usually has two parts. First, you figure out the odds of one specific outcome happening, and then you multiply that by the total number of ways that outcome can happen. The binomial theorem gives us that second part. It's the number of ways. It's the counting machine inside the probability machine.
For example, let's say you flip a coin 10 times. What are the odds of getting exactly 4 heads? Well, before you can figure that out, you need to know how many different ways you can get 4 heads. The binomial coefficient 10 choose 4 gives you the answer instantly, 210. Can you imagine trying to list out all 210 of those combinations by hand? No way!
And the story doesn't even stop there with whole numbers. The really huge leap came from Isaac Newton, who realized this pattern could work for fractional and even negative powers. That completely blew the doors open and created powerful new tools for whole new fields of math. So at the end of the day, the binomial theorem is way more than just some formula you memorize for a test. It started as a simple pattern in multiplication, but it turned out to be about counting, about combinations, and about the very core of probability. It really makes you wonder, doesn't it? How can such a simple pattern, one that people noticed centuries ago, still be such a fundamental tool for how we understand the world today? It's just a beautiful example of the elegant connections hiding all over the place in mathematics. Thanks for watching.